Hello, I'm going to speak to you today about two significant microphone designs which emerged about 50 years ago. The systems were devised in the 1960s, which was the infancy of high-quality microphone development. The capacitor system was already known, and I will say a few words about that before I deal with the Sennheiser MKH system. Microphones, as you are all aware, come in different designs. Essentially, the microphone does two things. It detects the compressions and rarefactions of sound waves in the air, and it converts its detections into an electrical signal. So how does the capacitor mic do it? By the way, when I joined the staff of the BBC in the 1960s, we were rapped over the knuckles for referring to condensers. A condenser is an old name for a capacitor, which is an electrical component capable of holding an electric charge. The mic we are studying today utilizes the storage of electric charge in its function as a transducer. Yet almost the whole industry calls these devices condenser mics. Well, I call them capacitor mics or capacitive mics because my knuckles still remember the 1960s. So what part does the capacitor play in the basic system? Well, imagine a capacitor which is charged by an electrical supply. It's a static event. Now, the capability of the capacitor to hold a charge is dependent on several factors. The main one, which interests us now, is the proximity of the plates which constitute its construction. So if we were to move the plates closer together, the device would draw more current from the supply. And were we to move the plates farther apart, the current drawn would reduce. Clearly then, if one of the plates was fixed and the other was free to be driven by the compressions and rarefactions of the air, a variation in the electrical current would emerge, which would be analogous with the sound which had energized the movement. In essence, that is the capacitor microphone. Now I must turn to the zeitgeist of these early developments. One of the dominant organizations in the manufacture of capacitor mics was, and still is, AKG, or Akustische und Kinogeräte Gesellschaft. And I should point out that AKG also manufactured dynamic mics, but it is the capacitor mics which interest us today. Capacitive mics were developed during the valve era. The transistor age had not yet dawned. Now, valve amplifiers have no problem with high impedance sources, and capacitor mics are natively high impedance. Consider this. Suppose we have a microphone whose capsule is in effect a small capacitor, let's say 40 to 50 picofarads. The impedance of a capacitor circuit depends on the following characteristics. The characteristics are symbolized as follows. XC is the impedance measured in ohms, 2 pi f, where f is the frequency measured in hertz, and C, the capacitance measured in farads. And the formula which puts these characteristics together is XC equals 1 over 2 pi fc. Now, you don't need to be an arithmetical genius to note this. It can be seen that as the frequency rises, the impedance falls, and it falls massively if the frequency is megahertz rather than kilohertz. However, when transistor amplifiers became available, their circuitry preferred a much lower input impedance, and there was much research into devising ways in which the high impedance of the capacitor mics could be matched with the low input impedance of the transistorized amplifiers. Several companies took initially the route adopted by Sennheiser in solving this conundrum. But the emergence of the FET, or field effect transistor, which mimicked the operation of the valve, made this ambition to match high with low rather unnecessary. You may be aware that if you connect a capacitor and an inductor in parallel, you create a tuned circuit. The circuit will resonate at a particular frequency. Let us say you choose values which result in a resonant frequency of 8 to 10 megahertz, say. 10 megs is well inside the range of frequencies which result in quite low impedance, friendly to amplifiers which utilize semiconductor technology, and well above the audible range. What if then the capacitor in this combination is the capsule of a capacitor mic? As the compressions and rarefactions of the air move the diaphragm backwards and forwards, the frequency will vary with the fluctuating capacitance of the capsule. This phenomenon is basically a modulation of the native frequency of the circuit. The fluctuations in the frequency of the circuit can then be detected as an audio signal. So there you have it. But you may have been asking how all of this detail is useful to the practical sound technician. Well, there is a lot more to say in terms of the practical application of microphones. Conventional capacitor mics have direct voltage sitting on the capsule of the microphone. In damp conditions, this voltage can leak in moisture droplets across the plates of the capacitor. This leakage causes bumps and crackles in the audio output. But with the RF system, this doesn't happen because there is no direct voltage on the capsule and therefore no noisy leakage. So, if you are working in high levels of humidity, an MKH will keep you out of trouble. Now, I usually ask you a couple of questions based on the content of my lecture. Name an element common to both the capacitor system and the RF system. And name a practical benefit which is offered by the RF capacitor system. Please keep a note of your answers. You have 30 seconds. I hope you've enjoyed this session, and if you have any questions about the content, please get in touch.